All right, so what is the velocity? Antiderivative of 0 is 0, and then you have negative 32t plus some constant vector, okay? And so you know v sub 0 here, if you plug in 0, is 0, 0 plus c1, which is, of course, your x1, y1. And so the velocity vector is x1, which is a constant, okay, and then negative 32t plus y1. And so what this is saying is the velocity at any point in the horizontal direction is simply x1. That is the initial component of that initial velocity. And then the second part is saying whatever the initial velocity in the vertical direction is, y1, you know, the thing is being shot up, not down. Y1 is a positive value, but then it's going to lose the vertical acceleration at a rate of 32 meters per second. Okay, so if you shoot this up at 32, if y1 is 32 meters per second, then in 1 second it's going to stop moving and then starts to go down. Right? And what I mean by stop moving is stop moving vertically. All right, so then that is my velocity. All right, let's try to find the position function, which is x1 times t now, right? And then you have negative. Now, what happens when you take the antiderivative of t? It becomes t squared over 2. So this is negative 16 t squared plus y1t. And let's put the constant vector outside. Okay, so you probably are familiar with this. It's not plus, by the way. It's, yeah, it is plus here. And so, you know, this is something that you may have seen even before you took calculus, like in pre-calculus class or something. All right, and so r sub 0, of course, this is 0, 0 plus c2, and that is x naught, y naught. All right, so here's your solution. R of t, this is the position function. That is x1t plus x naught, comma, negative 16t squared plus y1t plus y naught, right? And so that describes completely the motion of this object at any time t. So you could also describe here where you know the x naught, y naught are given. You don't have any choice on that one, but x1 can be written as the initial velocity, the norm of the initial velocity times the launch angle, cosine of theta, and y1 is the y component, the vertical component of the initial velocity, which is this magnitude times the sine of t, sine of theta. Okay, so that's you know, the solution here. All right, I'm going to do a specific example, but before that, let me just give you a little hint as you do your homework. Sometimes you have to find the maximum height. How do you find the maximum height of this object flying up in the air? You're trying to find someplace here, right? Well, right up here, there's something that's happening. What is happening in terms of this velocity at the very top? Very top means it stops going up and it starts to go down, right? So the y component, of the velocity, which is negative 32 t plus y1, becomes 0, right? So this is the y component of the velocity. That's what we mean by the object being on the top. So from this, t is easily calculated by dividing y1 by 32. And it makes sense, as I said before, if y1 is 32, because that component loses the speed at 32 meters per feet per second, you know, every second, this is the appropriate number for t. And so now you plug this t into the y in r of t, because y in the position function, which is this thing, okay, you plug that t in there, and then that will give you the height, or the y component, or the y coordinate, which is the height of this projectile at this time t, right? So that's not too bad. I will show you an example of this in just a minute. Sometimes it also describes the range. Where does this hit the ground? You know, if it's like a cannonball or something, how far does it go? At what point would it hit the ground? And so for this, what do you have to do? What's special about the point where the projectile hits the ground? Well, that's when the y coordinate, here, this goes to, it becomes 0, right? So let negative 16t squared plus y1t plus y, not, sorry about that. That's really not, it's really, I mean this one, right? Not this. That's not the position. This is the position function, and this is the y coordinate of the position function. So you want, let this be equal to 0 and find the appropriate t. Now notice here, this is a quadratic equation, t squared. So you'll find two t values. Okay, now one of them is the correct one, and it's going to be pretty obvious which one. For instance, in this case, one is going to be positive and one is going to be negative because you have to go backward in time to see when it would have hit the ground this way. So find the positive, value, the root of this quadratic equation, and then you plug this t into the x coordinate in R of t. So that's pretty straightforward, I think, right? Okay. So yeah, that's the problem here. Now I'm going to give you another problem. This will be a short part of this video. But here's the baseball problem. Oh, before that, let me show you something else too. Okay. So if a projectile is flying up in the air without the air resistance, so maybe it's flying in a vacuum, this is what it looks like, right? The picture of a projectile. Now the red arrows actually represent the velocity at each point. I want you to remember this, and because we'll be talking about this later with a worksheet. I want you to picture where the normal vectors are at each point. Okay, because normal is sort of like the second derivative, but the second derivative is the acceleration, which is very different. Okay, so when you take the normal vector, the unit principal unit normal vector, it's always perpendicular, pointing inwardly, right? So these blue arrows represent the normal vectors in as this object flies. All right. But what I want to express here, okay, so this is color coding. All right, so this is N, okay, and the red ones are T. Okay. And of course, you can talk about the binomial if you like. But what I want to show you here is that this gravity is always going down. Okay, so that's what G is, the acceleration. Acceleration due to gravity is always downwards, of course, because it's gravity. Right? So again, make sure you know the difference between the normal vector and the acceleration. The acceleration is the second derivative. Normal is not the second derivative, even though it is obtained by, differentiating, normalizing, differentiating, and normalizing. All right, so here's the question, and this is an example of a fictitious baseball stadium without any air. Imagine that, right? So I will pose the question and then let you work on that, and then we'll come back. Okay, so here's the question, right? So a baseball batter is hitting the ball, and the pitcher pitches the ball, and he swings at the ball. And today we have all kinds of analytics and statistics for any kind of swing. And let's suppose that this hitter or the batter hit the ball at the launch angle of 30 degrees, not unusual, and with a velocity, it's called the exit velocity of 128 feet per second. Okay, which by the way is equivalent to about 87 miles an hour. Not exactly a very fast exit velocity. It's not, a huge value, but it is a reasonable amount. Okay, now assuming that this place has no air and no air resistance, and therefore the baseball seams and the thickness of the seam and those are irrelevant, and the baseballs are not juiced, how far does it fly? Okay, and the question basically is this. Let's say from the home plate, the fence, the ballpark fence is at 350 feet away, which is sort of reasonable as well. And the height of that fence at that point is 10 feet. So it's a 10-foot high fence. And in order for this to become a home run, it of course has to clear the fence, right? And assuming that we don't have any incredible outfielder who is going to rob the batter of this home run and so on. Does this ball clear the fence and become a home run? Or does it hit the wall somewhere? Or does it hit the ground before the wall? Okay, so that's the question. Now you can use anything we did here. You don't have to recreate this procedure. In fact, you can go ahead and use this, right? And go ahead and use that and see if you can solve this problem. Of course, you want to use a calculator. And so the question here is this a home run? Okay. And what's the maximum height? Okay. And if it is home run, and if there is no fence, you know, how far does it fly? So this will be the distance. Okay. If you watch a baseball game these days, they have the exit velocity, launch angle, and for home runs, they will tell you the distance, which is like usually 400 feet or sometimes 450 and so on. All right, let's try to figure these things out. And then when you think you have the answer, you can come back.